This gigantic nuclear reactor in the sky fuels our planet. The sun derives its energy from nuclear fusion when atomic nuclei fuse together. Here on Earth, nuclear reactors work by splitting nuclei, the process of nuclear fission. But nuclear power comes at a price. All reactors generate nuclear waste, which must be disposed of safely to minimize the risk of harm from ionizing radiation. If large amounts of radioactive material escape, the results can be catastrophic, as we saw at Chernobyl. Besides nuclear power stations, nuclear waste also comes from isotopes used in research and medicine. The manager of this small research reactor at the University of London is Ian Sinclair.
On the top of the reactor, there are two movable shield doors. If you move these doors out and look into the tank, you can actually view the reactor whilst the reactor is at power.
The blue glow here is caused by high-energy electrons passing through the water. They are released during the fission process, and for a tiny fraction of a second are traveling faster than the speed of light in water. But it's inside the veins of the fuel elements where the nuclear fission reactions are occurring.
This is a full-scale model of one of our fuel rods. As you can see, it is basically an aluminium box, about 10 centimeters square and a meter long. The fuel for the reactor, that is the uranium, is incorporated into these uranium-aluminium alloy plates. This plate structure allows the water to be convected through the fuel to cool it. That water is also necessary for slowing down neutrons during the fission process. There are 24 of these fuel elements in our reactor core, and they are mounted vertically in the bottom of the tank.
When water is added to this lattice, neutrons are slowed down and the nuclear chain reaction diverges. To limit this increase, control rods are partially inserted from above. At the end of each working day, the reactor is shut down by simply lowering all the rods. Research here generates various items of radioactive waste, contaminated gloves, tissues, shields, and so on. This material is put into storage bins and is eventually transported to the National Disposal Service at Harwell. Samples from universities, hospitals, and industries come here to be made artificially radioactive, so that elements present in less than 1 part in a million may be identified. Here we can analyze the gamma-ray spectrum from the activated nuclear sample. Each element emits a unique set of peaks in the spectrum, a sort of nuclear fingerprint. And artificial gamma-ray sources from reactors are used for a wide variety of medical and scientific work. For example, in teaching. In the biology experiment at summer school, you yourself examined the effects of gamma radiation on the germination and subsequent growth of wheat seedlings. And you've seen how radioactive decay of traces of uranium in zircon crystals has damaged the surrounding mica crystal, and how precise measurements of parent and daughter isotopes can be used to date the Shap granite. Radioactive elements decay by emitting ionizing radiation, so let's just look at the different kinds. Alpha particles barely penetrate human skin. Beta particles, electrons, can easily be stopped, and lead sheets can stop X-rays too. But to stop high-energy gamma rays and fast-moving neutrons, you need a thick layer of lead or concrete. The source of all radioactivity is the atomic nucleus. This rare isotope of uranium U-235 is virtually stable, but it can be stimulated to decay by nuclear fission. When an additional neutron enters the nucleus, it triggers a total breakup. In less than a millionth of a second, it splits in two, emitting gamma rays and several neutrons, all moving rapidly apart. And since it was a neutron that initiated fission, if there were other uranium nuclei nearby, Some of these secondary neutrons could now go on to stimulate further fissions, and a chain reaction can happen. And some of these fragments are themselves radioactive. Here is nuclear waste in the making. And if more than one of the neutrons from the first reaction caused splitting of further uranium nuclei, then the chain reaction would accelerate, releasing more and more neutrons each time, and under certain conditions, an immense explosion would result. This effect can be simulated with a bunch of matches. A runaway chain reaction. For nuclear reactors, we need a more sensible arrangement, but now the fissile material is too spread out, so no chain reaction, it is subcritical. Adding more fuel gives a supercritical assembly, a chain reaction, not controlled, but far from being explosive. Holes in the fuel lattice now act a bit like control rods, so the fuel burns in a more controlled way. So, a reactor is a supercritical assembly of fuel with control rods absorbing enough neutrons to maintain a just critical chain reaction. And in thermal reactors like this, and the Sizewell PWR power station, water is essential to moderate the fission neutrons down to thermal energies. Drain the water, and the reaction dies. The earliest power reactors use graphite blocks as moderator. They work like this. Fast neutrons released by the fission process are progressively slowed down by bouncing of carbon nuclei in the surrounding graphite moderator. Slower thermal neutrons are much more likely to be captured by a uranium nucleus, and this increases the chances of causing further fission. All thermal power reactors use many hundreds of tons of uranium fuel during a working life of at least 30 years. Great care is needed when fuel rods are removed and fresh ones inserted. After perhaps 5 years in the reactor, only a few % of the uranium fuel has been used up, but fission products and heavy elements become significant neutron absorbers, and the whole assembly must be removed. The spent fuel assemblies are kept underwater at the power station for a year or so, while their intense activity dies down and their temperature falls. Then they are carefully transferred to 50-ton steel containers. Apart from the lid, they are made from a single piece of steel, over-engineered to provide a huge margin of safety. After careful cleaning and monitoring, the flask containing a couple of hundred spent fuel cans is filled with water, sealed and transported to Sellafield. Where once again it is stored in a huge cooling pond to await its turn for reprocessing for at least another year. Eventually, the fuel element is carefully stripped of its outer casing, which now is active metallic waste, while the uranium fuel pin is extracted so that it can be purified and recycled. The first stage is to dissolve it in boiling nitric acid. 6 tons a day is routine here. The result is a highly radioactive cocktail like this. Uranium is present here as the yellow uranyl ion, plutonium is green plutonium-4, and also present are various fission products. The basic fuel reprocessing problem is this: to separate these 3 components from the mixture. This is done by a series of solvent extraction stages by exploiting the differing solubilities of the 3 components in an organic solvent when the aqueous solution is agitated in contact with the solvent. Of course, it's not done in small batches like this, but in a continuous flow in which the organic solvent flows in one direction and the aqueous solution in the opposite direction. Here the pink fission products separate out to the lower aqueous layer. The whole process has to be carried out by remote control in permanently closed stainless steel tanks. The uranium is eventually solidified for reuse, but the unwanted fission products are pumped into shielded stainless steel and concrete tanks. Inside, A maze of 7 separate cooling coils remove heat from the highly radioactive liquid slurry. It will remain hot for over 50 years and must be continually monitored as the decaying nuclei slowly become less active. Eventually, this waste must be stored in a much more convenient form, glass. To do this, the waste is dried, mixed with 3 times the amount of silicate powder, and heated in a furnace to over 1,000 degrees Celsius. Just like nature's spectacular outpourings of volcanic basalt lava, it will be poured from a continuous furnace into stainless steel drums, a meter or so high. On cooling, it is very difficult to tell which of these is solid radioactive waste and which is 5-million-year-old volcanic glass. This slightly greenish one is the waste. After cooling, the drums are welded shut and stacked up to 10 high in air-cooled storage for another 50 years before final permanent disposal. It was announced in 1987 that in the UK, both intermediate and low-level radioactive wastes would eventually be disposed of deep underground, isolated from the surface environment. Here at Forsmark in Sweden, we have a view of such a scheme. The plan is to drive 2-kilometer-long tunnels from the power station under the sea. The repository is being built in 2 stages. First, 4 rock caverns and a deep silo for low and medium waste, mainly from Sweden's 12 nuclear power reactors. Later, another silo and more rock caverns will be added. The scale of the project is impressive. Each silo occupies a cavern 30 meters in diameter and 70 meters high. After excavation, a thick clay floor is laid. The silo itself is made of concrete and steel with walls 1 meter thick. It is divided into shafts 50 meters deep. A thick layer of fine bentonite clay both cushions the silo from the rock and also, when sodden, provides a virtually impenetrable barrier for further water movement across it. Special vehicles bring in concrete boxes of medium-level waste, and then remote handling machines deliver them to the appropriate shaft. Once full, the silo will be completely entombed in more concrete and clay to isolate the waste from its surroundings. Similar construction methods and remote handling techniques apply in this rock cavern. It has concrete cells and walls, and like the silo, is designed to store concrete boxes of medium-level waste. Low-level waste is stored in standard drums and skips in bare rock caverns. We dump many wastes, liquid and solid, into the surface environment. Here at Pitsea in Essex, huge amounts of non-radioactive domestic and industrial solids are disposed of. Added to this are quite nasty liquids, like waste acid from batteries, which is left to percolate slowly through the other wastes and eventually into the subsoil and rocks below. For many years, low-level radioactive solid wastes have been dumped here at Drigg, near Sellafield. Sooner or later it will be full, the first and probably last major surface radioactive disposal site in this country. Then all this type of material, as well as intermediate-level wastes, including the huge amounts of material which will be generated by the decommissioning of nuclear power stations, will have to be disposed of deep underground. A carefully planned operation started in 1987 to decommission, dismantle, and probably eventually remove all traces of the Windscale Advanced Gas-Cooled Reactor, classic symbol of nuclear power. and it is in the dismantling of nuclear power stations that the biggest nuclear waste disposal problem lies. Much of the steam-raising equipment has to be very well insulated. One of the biggest initial problems is to remove all the lagging safely, not because it is radioactive, but because asbestos was the chief component used here. Nowadays, very strict regulations govern the industrial use and disposal of asbestos. And of course, this problem also arises in decommissioning any power station, chemical plant, much of industry, and even domestic heating boiler houses. Inside the reactor building, everything is monitored for possible contamination, whether it be just a pipe junction or the interior of one of the large circulator electric motors. Some components definitely are contaminated, and protective polythene suits and sealed enclosures are necessary. Even here, though, conventional cutting tools can still be used. But it is in the dismantling of the reactor itself where new techniques had to be developed. Even after defueling, the core is still highly radioactive. The stainless steel in the middle is the hottest, then the steel of the pressure vessel. Even the concrete bioshield is radioactive. Getting the radioactive center out means building a sealed route in. Unfortunately, the heat exchangers are in the way, and they are contaminated too. The first job was to move them, and the only way they could go was up. Each having a mass of 170 tons, it took 3 days to raise them out of their concrete bioshields. The waste transfer route was open underneath. But now you need a remote control robot to do the job safely. A rotatable shield sealed to the reactor and a mast from which to work the robot manipulator, cameras, and cutting equipment. Then a building where the waste can go for packaging. The system is designed to work like this. The robot cutter slices off a piece of radioactive material. A robot hoist arm picks it up and carries it to what is grimly called the sentencing cell. There the radioactivity is measured and the waste allocated a rack. The whole operation, monitored by 6 TV cameras, is done by remote control. The rack is lowered into a concrete box, sealed with more concrete, and finally delivered to the outside world. The concrete boxes have been designed to survive accidents, just like any other container which carries radioactive material. All the contaminated waste will end up in 160 concrete coffins, destined eventually for storage deep underground. It is hoped by dismantling this reactor as a research project that the lessons and techniques learnt will lead to future reactor designs being more easily serviced and ultimately dismantled. Obviously, in these situations, great care is needed to limit and monitor the amount of radiation to which workers are exposed. But why can ionizing radiation be harmful? It can cause damage to the DNA contained in cells. If the DNA molecule is broken, it may rejoin, but the repair may be incomplete or incorrect, resulting in a change to the coded information passed on when the cell divides. Damage to DNA in humans may later result in the cells becoming cancerous. Ever since the discovery of X-rays, bodies have been probed with ionizing radiation, initially without realizing the potential dangers. Within months of the discovery, X-ray tubes were used to give pictures of astonishing anatomical detail. Metal objects like this ring showed up as easily as bullet fragments and wounded soldiers, even in the field. And when Pierre and Marie Curie discovered a new element, radium, which glowed in the dark, it heralded the nuclear age. In her words, this new source of light, the fruit of patient efforts of the scientist in the laboratory, will one day throw its rays on humanity and will give it consolation and alleviate its suffering. The Curie's refusal to patent the process for refining radium led to rapid commercial exploitation of radon, the radioactive gas given off by radium. A huge variety of bizarre appliances and treatments were marketed. You could give your drinks a sparkle with these, or use an emanator to bubble radon into your bath. And the mind boggles at radioactive corsets. Soon warning bells sounded as patients developed cancers and even died from excess radiation doses. Nowadays, the medical uses of radiation are much more controlled. Sophisticated scanning systems give more information with smaller doses. But always where radiation is present, we must balance the benefits against possible risks. Even so, things can go tragically wrong. In April 1986, one of the reactors at Chernobyl went out of control. The reactor core was exposed to the atmosphere. A plume of radioactive isotopes drifted around Europe for 10 days, leading to hotspots of radioactivity each time it rained. Chernobyl may cause tens of thousands of extra cancer deaths worldwide over the next 100 years, but because millions die of cancer every year, it'll be well nigh impossible to detect them. But many believe that where nuclear power is concerned, any risk at all is intolerable. Yet we all willingly face much shorter odds from other types of accident. Even 80 years ago, Pierre Curie, who daily experienced massive radiation doses, died in a road accident when only 46. While his wife, Marie Curie, was eventually killed by radiation, but not until she was 66. Today, your chances of being killed in a road accident are far higher than by radiation, natural or artificial. Smokers voluntarily run the greatest risk of all. About 1 in 3 cancer deaths are from smoking. And even for non-smokers, the next most likely cause of lung cancer is believed to be from breathing radon, the radioactive gas given out naturally from rocks and soil. Indeed, for most people, the average ionizing radiation dose is due mainly to natural sources. And taking a wider view, how do the hazards of nuclear waste compare with others? For example, with toxic materials in shallow dumps which may be released by future developments. With acid rain, which has caused ecological damage in Europe over recent decades. With the greenhouse effect, where carbon dioxide from fossil fuels and other gases threatens severe climatic change within a few decades. These and many other wastes are potential hazards for the 21st century. Science doesn't have simple answers to all these problems. We are into economics and politics here. But a good science background should help you make sound judgments about these matters, which will help to influence our uncertain future. In the brave words of Marie Curie, every civilized community has the pressing duty to watch over the domain of pure science, where ideas and discoveries are made, to protect and encourage the workers in its cause, and to give to them every facility. It is only at this price that a nation can grow and pursue a harmonious development towards a distant ideal.